All right, I hope you enjoyed that video from Marginal Revolution. I think that it's a nice explanation of the intuition behind consumer choice, the combination of the budget constraint and the indifference curves, and hopefully that was helpful for you. We're going to go on now to do some numerical examples of constrained optimization in this case, or utility maximization. And I want to teach you at this point a method for constrained optimization that you could apply to a variety of different contexts. So this is not specific to utility. It's not specific to economics. It's a mathematical technique to help us in situations where we're trying to optimize with a constraint. Okay, so it's called the Lagrangian Method, and once you get this method down, it's very simple to apply, not just for utility, but we'll use it later on in the course for profit maximization, right, and other things as well. Okay, so in this method, what we want to do is we want to combine our objective function, that's what we want to either maximize or minimize, with our constraint. And we do that by using what's called a Lagrange multiplier, which sounds complicated, but it's really not that complicated. So in this case, our objective function is going to be our utility function. We are seeking to maximize our utility, our happiness, subject to our budget constraint, right? Constrained by our income. And in order to combine those two, what we're going to do is we're going to rearrange the budget constraint so that it's equal to 0. And the generic form of that will be I minus px times x, minus py times y, right? So that should be equal to 0 at the optimum. And then we're going to just add it to our utility function, but it's multiplied by this lambda. That's lambda. And it's that is what we refer to as the Lagrange multiplier. All right, so we combine our utility function with our budget constraint. Then what we're going to do is maximize, and to find the maximum, we're going to take the derivative and set it equal to 0, right? We have two choice variables here. That's what we're choosing. That's x and y. And we take the derivative with respect to x and set it to 0. We take the derivative with respect to y and set it to 0. And then we can solve that system of equations to eliminate the Lagrange multiplier. So we have, at the end of the day, our optimal choice decision rule, okay, which I've called here the optimal consumption ratio, which will reduce to the marginal rate of substitution equal to the price ratio, okay? So that is going to tell us kind of the optimal ratio of x and y that we would like to consume. But you'll notice that does not depend on our income. So what we need to do to find how much we will actually purchase is then to combine the optimal consumption ratio with our budget constraint to determine our choice of x and y that maximize our utility. All right, so I know that seems like a lot of steps, but like I said, as you go through this a few times, it will become kind of second nature to you. So I want to go through an example here with some numbers to show you how this works. So we've got our utility function, we've got our budget information, and we want to combine all of them into our Lagrange function. What I want to do is I want to maximize my utility subject to my budget constraint. So I'm going to add on lambda times my constraint, which is rearranged so that it's an expression that should be equal to 0. And then underneath my maximization function here, I like to write my choice variables, my x and y. That's what I'm choosing in order to maximize my utility. So this is how we write out our Lagrange maximization problem. And to solve it, the first step is to find the first order conditions, which means to take the partial derivative with respect to both choice variables. So I like to write here first order condition with respect to x and respect to y, just to keep everything straight. So when I take the derivative with respect to x, I get 16xy squared minus lambda, and I'm going to set that equal to 0. Because in order to find the maximum of a function, remember we want to set the slope equal to 0. And so the intuition here is that we take the derivative, we set it equal to 0, and that helps us find our maximum utility or our optimal choice. All right, so for our derivative with respect to y, we've got 16x squared y minus, now I've got 4 lambda equals 0. So I set that equal to 0, and I've got both my first order conditions written out here. Now the next step after I've taken the derivative is to combine the first order conditions in order to get rid of the lambda. So here I'm going to combine these, and I'm going to do that by basically like dividing them, okay? And I want to move the lambdas over to the other side of the equation and then divide. So what I really have here, right, is I have 16xy squared equals lambda, and I have 16x squared y equals 4 lambda. And then I'm going to imagine I'm just dividing these functions. And what you'll notice is that really what this is here is my marginal rate of substitution. And then on this side, I have my price ratio. Because the marginal rate of substitution is the slope of the indifference curve, and the price ratio is the slope of the budget constraint. So this will tell me where my indifference curve is tangent to my budget constraint. Okay. All right, so simplifying this, you want to use the same kind of technique that you use to simplify your marginal rate of substitution, dividing to simplify the terms. So 16 and 16 cancel out. X divided by x squared, that's an x on the bottom, and then I've got a y on the top. The lambdas are going to cancel out, and I've got 1 over 4. So here I have my optimal consumption ratio. Again, remember this does not depend on income, but it gives me the condition for the tangency between the budget constraint and the indifference curve. Where exactly I consume is going to be determined by the budget. So we need to now combine this optimal consumption ratio with our budget constraint to solve for the actual values of x and y that we would like to purchase. So to do that, I'm going to solve this optimal consumption ratio for one of the variables, right? That's easy. And then I'm going to write out my budget constraint. That's 200 equals x plus 4y. Oops. And now I can just plug that into my budget constraint and solve for x and y. So I've got 200 equals x plus 4 times 1/4 x. So that's 200 equals 2x. And my optimal choice for x will be equal to 100. And then to get the optimal choice for y, I can just plug that back into this optimal consumption ratio or the budget constraint. Both will give you the same answer. Here I have y is equal to 1/4 times 100, so that's 25. Right, so the choice of x equal 100, y equals 25 will maximize this consumer's utility. Now the next thing that I want to do is I want to be able to show that on the graph and to show the tangency between the budget constraint and the indifference curve so that I know that what's happening with these numbers, right, has some meaning to it. So let's go ahead and graph the budget constraint. It's always a good idea to just graph the budget constraint first and then just draw on the tangency with the indifference curve. So again, my budget constraint is 200 equals x plus 4y, but for the purpose of graphing, I want to rearrange that so it's y equals some function of x. So I've got 4y equals 200 minus x. So y is equal to 50 minus 0.25x. So my budget constraint here will start at 50 and then go down to 200. And my optimal choice, in this case, it's exactly in the middle of the budget constraint. And that's actually the reason for that is because you see the exponents here are equal to each other. And so I actually end up spending, half my money on each product. So I've got 125. That's my optimal consumption bundle. And then, like I said, you can draw your indifference curve kind of just on there. It's a Cobb-Douglas utility function, so I know my indifference curves look like those nice convex indifference curves. There would be some other indifference curves here, higher and lower, but you can see because utility increases as I move out this way, that this curve is the highest possible curve I can be on within my budget set. So I've got that drawn here, and the last thing that I want to do is to label my indifference curve with the utility that I've gotten from this bundle. So in this case, I can just plug my optimal consumption bundle back into my utility function. I get u equals 8 times 100 squared times 25 squared. It's going to be a big number that turns out to be 50 million. Okay, remember that number is kind of meaningless apart from the fact that it indicates that we're on this specific indifference curve. All right, good. So we're done.